Hello everyone, here I'm going to explain a high-efficiency DC to DC buck converter that I designed using an Arduino Uno. Well, see, I can be used to manually step down 12 volts to 5 volts or any voltage between 0 to 12 volts using a potentiometer, and explain how the internal components work. I'll also show how you can use my custom online calculator to pick the perfect parts for your specific buck converter project. Let's look at the circuit. We are using a P-Channel MOSFET IRF4905 as our main switch. Because the Arduino can't handle 12 volts on its pins, we use an NPN transistor, 2N2222, and a pull-up resistor to safely drive the MOSFET gate. When our Arduino sends a PWM signal, it toggles this MOSFET on and off thousands of times per second. But a raw PWM signal is just a series of square waves. To get a smooth DC voltage, we need three critical components. L1, the inductor. This is the heart of the converter. It stores energy in a magnetic field when the MOSFET is on and releases it to the load when the MOSFET is off. It resists sudden changes in current, smoothing out the choppy PWM. C1 output capacitor, while the inductor smooths the current, C1 smooths the voltage. It acts like a reservoir, filling up during the on cycle and discharging during off to keep output steady. C2 feedback filter. This small capacitor is often overlooked. It creates a low-pass filter without feedback resistors. This prevents high-frequency noise from reaching the Arduino's ADC, ensuring our voltage readings stay stable and don't jump around. You can't just pick any inductor or capacitor. The values depend on your switching frequency. For this demo, we are running at 32.25 kHz. To find the right values, you need to know your input and output voltages, your maximum load current, with design for 2 amps, and your ripple factor, which is usually 30%. Instead of doing the heavy math by hand, I've developed this interactive buck converter calculator on my website. You just enter your parameters, like our 32.25 kHz PWM switching frequency, input and target output voltages, maximum load current, ripple factor, and we can also provide the feedback resistor values R1 and R2, and it instantly gives you the required inductance and capacitance. For this high-frequency setup, we've used a 155 microhenry inductor and a 47 microfarad capacitor. The Arduino also needs to see the output voltage to display it. Since 12 volt would damage the Arduino, we use a voltage divider with R3 14K and R4 10K. The formula to calculate what the Arduino sees is Vout times R4 takes R4 over R4. In our code, we simply multiply this back by the inverse ratio on the hero monitor. Now let's see the theory in action within Proteus. Keep an eye on the serial monitor as I turn this 10K ohm potentiometer. Notice how the duty cycle, or the PWM value, changes in real time. As I rotate the pot, we are increasing the on time of our MOSFET. This allows more energy to be stored in the inductor, and you can see the output voltage clang smoothly on our virtual voltmeter. Let's look at the signal waveform before the inductor and compare it to the output on the oscilloscope. The waveform before the inductor is a sharp square wave, switching rapidly between 0 volt and 12 volt. But look at the output signal waveform. It's a beautiful, smooth DT line that shows our filter is working exactly as intended. Now let's see what happens if I remove the capacitor C1. As you can see, the output voltage starts to fluctuate wildly. This is because while the inductor handles the current, the capacitor is needed to act as a reservoir to maintain a steady voltage. Without it, the switching nature of the circuit becomes visible as ripple noise. Let's put it back in. As you can see, C1's role is to filter out that remaining ripple, absorbing the switching energy and turning it into a steady, reliable DC output voltage. Thanks to this stability and our C2 feedback filter, the Arduino can accurately monitor the output. Even though we're switching at 32.25 kHz, we have a rock-solid power supply ready for any project. And there you have it. A working buck converter controlled by an Arduino. You can find the full schematic, the Arduino code, and the online calculator at the link in the description below. If you found this helpful, don't forget to like and subscribe for more electronics tutorials. See you in the next one.